Okay, so our next unit that I'm going to begin now is on the concept of connectivity. So we already know what it means for a graph to be connected. Of course, a graph is G is connected if for any two vertices of G, say U and V, there's a walk from U to V. Now, that basic concept of what it means for a graph to be connected is very important. Of course, it's easy to think about. A graph breaks up into connected components. But there are higher orders of connectivity. So instead of just being connected, there's a way for your graph to be two connected or three connected or four connected. And so it's another parameter about a graph that we're going to be introducing, but it's a very important one. We will see that this parameter has several, well, at least a couple of very nice interpretations. So there are a couple of different ways to think about it. And it's a hugely important a property of graphs, how well connected they are. I'll say, so, I mean, I'm a graph theorist. This is what I do for a living. I think about connectivity all the time. I mean, when we get a graph, it's a thing that you just want to know. How well connected is your graph? It's just a very relevant feature when you're trying to prove theorems about graphs. But it's also a thing that's incredibly useful in applications. So, graphs, they're just abstract networks. When you have a network, so maybe you have some important little network of things that you need to move between. If you have two nodes somehow in the middle that fail, if you suddenly can no longer get from one node to another node in your network after there are a couple of failures, that's a lack of robustness, right? That's telling us that your network is somehow not as robust as you might want it to be. And that's the notion of connectivity. So so what we're going to prove, what we're going to move toward eventually, are a couple of very important theorems due to Menger that have really, really profound importance in graph theory, and also they're richly important in understanding kind of robustness of networks, which is just a thing that you care about if you're going to apply graph theory somewhere, almost anywhere, I would say. Right, so that's connectivity. Now we're going to get started here a little bit slow. I will say that the eventual proof that we get of Menger's theorem is almost too quick. It's going to be, it's like, it's a little slick. And so part of the reason that we're going to spend a little bit of extra time on two connectivity is actually to do a couple proofs in a little bit slow motion, just so we get a better feel for this parameter. I could somehow be a little bit more efficient in teaching this material by kind of flipping things and giving you a super slick proof, but I'd rather not. I'd rather kind of go slow. Let's build up and talk about two connectivity. So anyway, so that's why we're doing what we're doing. I'm going to start off by introducing a concept that is not in every graph theory book, but I personally find it very, very useful. My PhD supervisor spends more time than anybody I know thinking about connectivity of graphs, and this is his favorite way of operating with them. So I'm just going to draw you a picture of what we're going to be doing. So the picture is somehow where everything is going to come from. And then I'll introduce the formality after the picture's in place. So here's the idea. I want to think about taking a graph and kind of splitting it into two pieces. But there are going to be some vertices in the middle. So I'm going to take a graph. Maybe there will be 4 vertices that I'll put in the middle. And now I'm going to do, well, it's a little bit of a funny thing. I'm going to draw over here a kind of bag. And over here, I'm going to draw a bag. And what are we going to have now? Well, okay, maybe I'll make these vertices a little darker so you can see them better. So now, the whole rest of the graph is going to go in these bags. And so you can have more vertices over here on the left and some more vertices over here on the right. And all the graph that you draw has to stay kind of within these two bags. Now these bags, there's no rule that these bags don't have to be, you see here my bag on the right, it actually has a disconnected part. So the graph I've given you isn't even a connected graph, but that's okay. What I want to do is I want to formalize this concept. So this is what we're going to be calling a separation. And again, the way I'm going to think about it and I'm going to describe it is I'm going to think about having a graph. I'm going to have a collection of vertices that are kind of in the middle, and then my graph is going to be split by that set of vertices. So there's going to be a bag of graph on the left and a bag of graph on the right. Those two bags are allowed to share the vertices in the middle, and all the rest of the graph kind of lies in those two bags. Right, so this is the way I'm going to be operating. And we can see, of course, that if you delete the vertices in the middle there, then what's left of your graph, at least if you've got a vertex on the left and a vertex on the right, then what's left of your graph after that deletion is no longer going to be a connected graph, right? The main feature here of these two bags is what? Well, you're not allowed to have an edge that goes from a vertex that's in the bag on the right, not in the middle, but properly on the, this is your left. You're not allowed to have one that goes from a vertex that's properly on the left-hand side to one that's properly on the right-hand side. Right, so you're not allowed to have edges like that. So what that means is that if you do delete the vertices in the middle, well, if you've still got a vertex on the left and you've still got a vertex on the right, then now your graph will not be connected. So when we're doing this separation, we are seeing a way, at least if there's a vertex properly on the left and properly on the right, in that case, we are seeing a way of disconnecting our graph by deleting the vertices in the middle there. And that's frequently what we're kind of going to look to do. The reason I'm introducing this notion of a separation is that it's very convenient when we're actually going to prove things. So it's a really nice thing to say, hey, let's take this separation. I've got this graph on the left, I've got this graph on the right, and we'll go and operate with them. So it's sort of like there's just a bit of convenience here, kind of operationally. It's just giving names to the right objects that will allow us to manipulate and prove our theorems efficiently. So okay, so let's get these let's get these things in place. Let's formally define things. So as I said, I'm going to be formally defining this object as a separation, and I'm going to be constantly thinking about this. I'm going to be thinking about taking your graph, putting some vertices in the middle, and having two bags. Now, when we say a separation, what we're going to mean formally is what? Well, I'm going to give a name to the subgraph consisting of the bag on the left, and it's including the vertices in the middle. So it's all the vertices on the left and in the middle and all the edges over there in that bag. That's going to be one subgraph, and then there's going to be one for the right-hand side. So a separation of order K in G is a pair of subgraphs. I realize I'm going to run out of space. Let me even shrink that a little. So separation of order K in G is a pair of subgraphs H1, H2. And again, in my picture, let me go ahead and draw it. In my picture, I feel like my green bag is getting confused, but this might be H1 and this is H2. So I'm thinking of H1 as the graph that's given by that bag on the left. So the graph that's sitting in that bag on the left. H2 is the graph from the bag on the right. So a separation of order K, in my graph G, it's going to be a pair of subgraphs, and they're going to satisfy some properties. Ooh. You may not be able to tell the difference between these colors, but I'm amusing myself by switching between them. So what properties are these things going to satisfy? Well, what properties do those two bags satisfy, right? So I've got I've got this subgraph H1, that's my bag on the left, subgraph H2, that's my bag on the right. And what properties are those two subgraphs going to satisfy? Well, one property is that when you take the union of H1 and H2, the union of those two subgraphs, that's the original graph. So H1 union H2 equals G. There you are. Second up, well, the bags, they're overlapping on those vertices in the middle, but they're not overlapping on any edges of the graph, right? Every edge of the graph has to be in the bag on the left or the bag on the right, but not both, right? So when I tell you the union of H1 and H2 is G, well, now you know, so every edge of the graph has to be in H1 or H2, but also you're not allowed to have them sharing edges. An edge has to fall in the bag on the left or in the bag on the right, and that means that we should also have the property that there's no edge in common to the two. Right, so they don't share any edges. So now we're in a good shape. Now we've got something that already looks pretty close to what we were aiming for, right? We have a bag on the left, bag of graph on the left, bag of graph on the right. Their union is the whole graph. So when I put them together, I got the whole graph, and every edge has to be in one of the two, but it can only be, it's in exactly one of the two. So it's not allowed to be shared between the two. So that really means I can draw this bag on the left, I can draw this bag on the right, and put my graph down. There's only one other property here. You see there's a parameter in my definition. We have a separation of order K. Well, K is going to be the number of vertices in the middle. So when I just say a separation, I could mean a separation of any order, but if you want to specify a separation of order 3, that means you should have 3 vertices in the middle. So the number of vertices that are shared in both H1 and H2 is exactly equal to K. And so our picture up here, in this picture, I'm showing you a 4 separation of a graph. Yeah. This is a separation of order 4. Right? So again, a separation of order 4. I mean, informally, I'm just thinking about, you're taking your graph, you've put it into 2 bags that share 4 vertices in the middle. More formally, a separation of order 4, it's going to be a pair of subgraphs. You're going to have a subgraph on the left, H1, a subgraph on the right, H2. The union of those 2 subgraphs is going to be the whole graph. So every vertex and every edge is contained in H1 or H2 or both. The edges of H1 intersect the edges of H2. That's empty, so every edge is in exactly one of the 2. And the number of vertices that are shared, so they're allowed to share vertices, but the number of vertices that they will share would be 4 if you have a separation of order 4. Right, so the separation of order 4, it's kind of indicating a way that we could, I mean, if you like, it's kind of indicating a way that you could remove those 4 vertices in the middle and separate the graph. But it's a nice sort of thing to look at, and this notion of separation is going to be very efficient for us when we go to when we actually go to operate with it. So the downside of this definition is just that it comes with a lot of a lot of complexity itself. Like this separation, it takes a little bit to define and understand. But I find it works very well if you have this concept in your head that you're just putting your graph into two bags that share a set of vertices in the middle. I find that's pretty easy to understand. If you can wrap your head around this formalism, then we'll really be off to the races. There's only one more notion I need here. Remember when I was talking about actually disconnecting the graph? So separations, we're allowed to have separations. And let me draw another one just to have something else to look at. So yeah, I'm going to draw a pretty boring separation here. So this is going to be a 3 separation of a graph, but it's going to be especially boring. I'm going to have over here, there'll be a loop on that vertex, an edge here. Now, in this separation, so this is a separation that's order 3, right? So here I have 2 bags of graph. I've split my graph into 2 bags, right? This is a separation. It's order 3 because there are 3 vertices there in the middle. Now, remember when I talked about disconnecting a graph, there was a little caveat that I introduced. If you have a separation of say order 3, and there's a vertex properly on the left and there's a vertex properly on the right, by which I mean in the bag on the left but not in the middle, and in the bag on the right but not in the middle, well then when you delete those 3 vertices in the middle, you will have disconnected your graph because you won't be able to get between those 2 vertices, right? However, it's possible that you just don't have a vertex that's in the bag on the left that's not in the middle. And that's what you're seeing over here in this example. So I'm drawing a separation of order 3, but you can see that, well, all the vertices that are in that bag on the left, they're actually in the middle of the graph. I mean, there are a couple edges over here that are in the graph on the in that bag on the left, but if you were to delete those 3 vertices in the middle that are shared by my 2 subgraphs here, you don't actually disconnect the graph, right? You're still left with a connected graph. In this case, you're left with a connected graph that looks like it's a triangle. It's a complete graph on 3 vertices. So because you don't have a vertex properly on the right and properly on the left, you end up with this feature that your shared vertices, the vertices that are in the middle of your separation, they don't actually disconnect the graph. Deleting them doesn't actually disconnect the graph. And that's going to be an important thing for us to take note of. And so accordingly, we are going to give it a name. We're going to give that concept a name. A separation is proper if there's a vertex properly on the left and properly on the right, by which I mean in the graph on the left, but not in the middle. So this separation is proper if, so I want to say there's a vertex on the left, but not in the middle. So I can say the vertices of H1 that are not vertices of H2, that's not empty. And similarly, there should be a vertex in H2 that's not a vertex of H1. Whoa. Right, so our separation is going to be a proper separation if there's a vertex that's in the graph on the left but not on the right, and one on the right but not on the left. So in that case, again, if you take those vertices that are in the middle that are shared by the 2 subgraphs and delete them, you will have disconnected your graph. So I think of a separation usually as kind of a way of separating a graph. We're sort of indicating some way that you can take your graph and kind of split it into two pieces. But you do have to remember that a separation can be improper. It might well be that I show you a separation, and in fact there are no vertices in the graph on that left hand side of the separation that are not also in the right. It's just a kind of degenerate degenerate thing that can happen, and as usual in math, we are going to admit the degenerate case in because it makes our arguments more natural. Let me introduce one other caveat here that I maybe should have said at the start. Now that we're going to go start talking about connectivity, we're really not going to be interested in graphs with loops. So for the whole purposes of this section on connectivity, we're just going to assume graphs are loopless. So maybe in accordance with that, I'll go down and delete that loop that I added down there. You can define the concept. I mean, loops are just mostly an annoyance when you're going to think about connectivity. They don't contribute anything to the notion. So this is more out of convenience because it just simplifies some of the language, and it's not losing us anything. So right. So again, our graphs are going to be loopless. We've now introduced this very important concept, that of a separation. Again, I think if you want to think about this, it is easy to think about taking a graph and splitting it up. There's a bag of graph on the right, a bag of graph on the left, and they share some vertices in the middle. It's an easy thing to think about. What I want you to do is take a moment and recognize that picture is going to be naturally formalized by me giving you a pair of subgraphs H1 and H2 that satisfy these three properties. So the union of H1 and H2 is the whole graph. There are no edges in common. So we're seeing our whole graph with the left and the right. Every edge is either in the left or on the right, but not both. And if it's a separation of order k, then you should have k shared vertices. And again, usually when we're thinking about this, we're thinking about those k vertices in the middle as k vertices that we could remove and separate what's left of the right from what's left of the left. But that only really gives you, that only actually disconnects something on the right from something on the left if you have a proper separation. If you have the property that there's a vertex that's on the left but not the right, and on the right but not the left. Okay, good. So that's our main new concept. And just for starters, we're gonna do a couple of very easy observations about this. Boy, I'd love to keep this. Oh, let me keep it around a little bit. Let me just keep this definition on the page. Usually when you teach, it's nice to have a blackboard and keep a definition up on one place while you sort of carry on somewhere else. My ability to do that here is very limited. Okay, but I'll do the best I can. So our first observation is that your graph G has a proper separation of order 0 if and only if G is disconnected. No, this is a thing we, hopefully you just recognize this. Now, if you have but it's, so hopefully this is sort of easy to see, but maybe it's worth taking a moment to kind of point out some of the nuance here. Now, if you have a graph that has a separation of order 0, then it is certainly disconnected, because you found your graph has a subgraph H1, that's the graph on the left, and a subgraph H2, that's the graph on the right. They don't share any vertices, and there are no edges that are allowed to go from H1 to H2. So certainly, if I give you a separation of order 0, then your graph is going to be disconnected, right? So that's the only if here. So a proper separation of order 0 implies that your graph will be disconnected. Let's go back and think about the if. Now, if your graph is disconnected, then what we know about it, well, we know how to think about this, right? When I give you a graph that's disconnected, the first thing you're going to say is, well, let's consider the connected components. Now, if I gave you a graph that's disconnected and it had 2 connected components, well, you can call one H1 and one H2, and there you are. That can be your separation. That gives that pair of subgraphs is a separation of order 0 in the graph, right? Those are 2 subgraphs. Their union will be the whole graph. There are no vertices. There are no edges in common, because I've told you it's a separation of order. Well, these 2 subgraphs actually have no vertices in common, and that means that condition property 2 is going to be satisfied here, and property 3 is going to be satisfied for k equals 0, right? There are no vertices in common. So, so again, if I gave you a graph G with just 2 components, I can call one H1 and one H2, and that pair of subgraphs is going to be a separation of order 0, and it's going to be a proper one, right? There's a vertex in H1 but not H2, and H2 but not H1. So if I gave you a disconnected graph with just 2 components, then it's very clear what this 0 separation should be, just those 2. Now, what if I give you a graph that is disconnected, but it has, say 5 connected components? What is what's the separation of order 0 that we're going to, or the proper, what proper separation of order 0 are you going to have? So suppose let me just draw a picture. So, so I'm drawing, sorry, I'm really trying to optimize space. I should have maybe just made the only if is kind of easy. So let's draw a graph. I'll just draw something. G1, G2, G3, G4, G5. Okay, so I'm just drawing a graph with 5 components. G1, G2, G3, G4, G5. Those will be the 5 connected components of my big graph that I'll call G. What are the 0 separations of this graph that I'm describing here? This might be worth just taking a moment to pause and think through what the answer is. It's not hard. I'll give you a second to do that, or you can pause the video and do that if you like. Okay, so if you figured it out, great. If you're just listening along, the answer is, well, if you want to make a 0 separation, it's just consisting of 2 subgraphs, right? I mean, you've given me 5 connected components, but somehow I have to report back 2 subgraphs. Now, the 2 subgraphs that I have to report back, if I want to give you a 0 separation, they're not allowed to share any vertices, but the union of those 2 should be the whole graph. So what can I do? Well, I can take these 5 subgraphs and I can divide them into 2 sets however I want. Any of those things would be a 2 separation. So for instance, here I could take these 5 and I could put G1 as the graph on the left, and G2 union G3 union G4 union G5, that could be my graph on the right. That would be a perfectly valid 0 separation, and it's going to be a proper 0 separation because, when I tell you G1 as a connected component, it's automatically non-empty, right? So you'd have a vertex properly on the left and properly on the right. So if you give me a graph that is disconnected, then it has 2 or more connected components, and however you'd kind of file those, just split them so that there's a non-empty collection of connected components on the left and the complementary non-empty collection of connected components on the right. However, you divide up those connected components into two non-empty groups, well, that's going to give you a proper zero separation. So I'm not, I don't even know. I mean, I'm just going to write the if portion we've just verified in saying this. This is not a difficult observation. I don't think I actually write much. Oh, I'm sorry. I'm looking at it. Yeah, I don't actually give any sort of proof in the notes. It really is coming straight from the definitions. But it is maybe worth noting here. If I'm giving you a disconnected graph, usually the thing that you go to very quickly is to say, well, let's just talk about all the connected components. And it is a little bit different than an actual a zero separation. Right? So a proper zero separation, you're just splitting the graph into two pieces, not into many. And that's kind of the main difference at play here. One of the things that's kind of nice about the concept of a separation is that, well, in lots of cases, when we're doing our proofs, it's convenient just to split things into two pieces. Why have to deal with more pieces? Why not just sort of file things into a left and a right? It's usually kind of the right thing to focus on for us. Okay, so your graph is going to have a proper zero separation if and only if it's disconnected. Yeah, I'm liking keeping this definition of zero of separation on the page. So let me try and erase that observation and keep this definition around, and we'll do one more easy observation. I wonder if I can. Oh yeah, why don't I do the following? Why don't I even just shrink this a little? Okay, so another definition. I will declare a vertex V to be a cut vertex if when you delete it, the number of components in the graph goes up. So I'm going to have a cut vertex if when you delete it, the number of components goes up. The number of components of G minus V is greater than the number of components of G. So that as well aligns with what our notion of cut edge is. Now, I think when we actually defined cut edge, we declared an edge E to be a cut edge if it was not contained in a cycle. But then we proved that, well, if you take an edge and you delete it, if it's a cut edge, then the number of components goes up by 1. And if it's not a cut edge, then the number of components stays the same. So it's also true that an edge E of your graph is a cut edge if and only if, when you delete that edge, the number of components of the graph goes up. So that aligns with this concept of cut vertex. Of course, when you delete a vertex from a graph, the number of components could go up by a lot. If you want to imagine a graph that's just a star here. So this, I think this is K1, 8. So there's a bipartite graph where there's one vertex on the left side and 8 on the right and all possible edges in between. This graph, of course, if you delete that middle vertex, that degree 8 vertex, then you're going to go from a connected graph, a graph with 1 component, to a graph with 8 components. So unlike cut edges, if you have a cut vertex, when you delete it, the number of components could go up by a lot. But otherwise, this is kind of aligning with what we saw in the setting of cut edges. Now an observation. So if I give you a graph G that is connected, and I give you a vertex V, that vertex is going to be a cut vertex if and only if there is a proper one separation, H1, H2, the pair of subgraphs, where your vertex V is the unique vertex in common in those two graphs. So the vertex V is the only vertex that's in both V of H1 and V of H2. So if G is connected and V is a vertex of G, then V is a cut vertex if and only if there is a proper one separation, H1, H2, with V of H1 intersect V of H2 equal your vertex V. Right, so your graph is going to be your graph. So your connected graph G is going to have the vertex V as a cut vertex if and only if there's a proper one separation H1, H2, so that V is the unique vertex in both of those. And let me go ahead and draw my picture. I'm going to draw just down here on the right in the interest of saving space as best I can. So there's going to be a bag of graph on the left and a bag of graph on the right, and the vertex V, there it is. It's the unique vertex in both, and there'll be some graph over here on the left and some graph over here on the right. So that's what a proper one separation looks like, right? So it's going to be a bag of graph on the left, bag of graph on the right. They're going to share a unique vertex in the middle, and there should be some vertex in the left but not right, and right but not left. So there's so that's just by definition what a proper one separation is. I'm drawing the example here. Of course, it's very easy to see that if you have a proper one separation, then when you take the vertex V and you delete it, well, you're no longer going to have a connected graph, right? Because if you have a proper one separation where V is the unique vertex in the middle, then when you delete the vertex V, because it's proper, you're going to be left with a vertex over here on the right, you're going to be left with a vertex over here on the left, and there will be no path between them. So if I give you a proper one separation and V is the vertex in the middle, then V is a cut vertex. So we've just verified, I mean, in saying that, I'm just verifying the if direction. All right, we've just verified if you have a proper one separation where V is the vertex in the middle, then when you delete the vertex V, oh, sorry, in a connected graph, if I gave you a connected graph and you have a proper one separation where V is the vertex in the middle, then in fact V is going to be a cut vertex, because when you delete it, you started with a connected graph, and after you delete it, then you're no longer going to have a connected graph. So that's the if direction. How about the only if? So for the only if, I'm now giving you a vertex V, and I'm telling you that V is a cut vertex. Well, if I've told you that V is a cut vertex, that means when you delete V, you're going to have more than one component. Sorry, right? The graph G is connected. So my original graph G is connected. I'm giving you a vertex V, and I'm promising you this is a cut vertex. That means when you delete it, you started with one component, but you're now going to have two or more. So what I can do here is just like what we saw in the setting of the zero separations. In fact, maybe what I'll do is I'll kind of lean on the picture because I can't do much otherwise. So I'm going to draw right now the graph G minus V. The graph G minus V is going to have some components, maybe G1, G2, G3, G4. Maybe those are my components of G delete V. What I know is that G delete V is going to have two or more connected components, because my graph G was connected, but G delete V has to have 2 or more components. So there's G delete V. Now what I'm trying to do here is I'm trying to show you that my cut vertex V also appears as the unique middle vertex in a proper 1 separation, right? So we're trying to prove the only if direction of this observation. So we're trying to prove that if I hand you a vertex V that's a cut vertex, then you can show me a proper 1 separation. You can find a left graph and a right graph that are intersecting only on that vertex V. And this argument is actually a lot like the 0 separation case here, a lot like that our first observation. We can kind of operate in G delete V, right? What happens when you look at G delete V? Well, you've got these 4 connected components. So let me now return to the original graph G. So let's put the vertex V back in our picture. I'm going to put the vertex V back up here. Now, when I return to my original graph, what's going to happen? Well, we're putting back the vertex V, and V is incident with some a whole bunch of edges. Where do those edges go? Well, the other ends of those edges have to be in G1, G2, G3, or G4. Again, I'm assuming loopless. And in fact, because my original graph is connected, you better have at least one edge headed to G1 and at least one to G2 and one to G3 and one to G4. So that's what my original graph looks like. I don't really know how many edges go between V and each component GI, just that it's at least one. But anyway, I can draw a picture that's pretty helpful here. And again, the main thing that I know is that I have at least 2 of those components when I delete V, and that means that I can split them into 2, partition them into 2 non-empty groups. So here I'm going to group G1 and G2 and G3 and G4 and show you a 1 separation. So what we're going to do here is this guy and this guy. So what I'm doing now, I'm just showing you my 2 bags of graph. So this is going to be the bag H1 and this is going to be the bag H2, by which I mean the subgraph H1 and the subgraph H2. So I'm just showing you 2 subgraphs of my graph, H1 and H2. You can readily verify that H1 and H2 as a pair is going to be giving me a proper 1 separation, right? So, I'm just drawing the picture here. I'm not arguing this formally, but the formal proof should be fairly easy to see how to write down, and it's impossibly tedious for me to write down on this medium. But again, what we've done, when you delete the vertex V, you have 2 or more components. I can divide those into 2 non-empty groups. I add the vertex V back and think about this original graph. And well, I'm going to make 2 subgraphs of my original graph by taking the first group of components of G delete V plus the vertex V and all edges between those components in V. That's a subgraph H1. I'll do the same on the other side. That's now giving me these 2 subgraphs, H1 and H2. Because I grouped my components of G delete V into 2 non-empty groups, I know that separation that I get, so I'm going to get a 1 separation, and I know that separation is going to be proper. And so this is completing the proof. So if I had given you a cut vertex of the graph V, so I've given you a connected graph and a cut vertex of that graph. Sorry, let me say that again. If I give you, that's right. If I give you a connected graph and a cut vertex V, then you can find a proper 1 separation of the graph where V is the unique vertex in the middle. And yeah, I think these separations, as you start to work with them, it's a little bit, it takes a little bit of thinking just to get straight this definition. I mean, it's just a definition with several aspects to it, but once you get it in your head, it really is pretty natural. And I find that it's actually the way you want to draw pictures of graphs. What I really like about this is that It's just the way you want to draw things. You want to think about taking a graph and splitting it into two pieces. That's H1 and H2. We're just formalizing what that right notion should be for taking a graph and splitting it in two. And we've now made a couple of nice observations. We have that a graph has a proper zero separation if and only if it's disconnected. And for a connected graph, if I give you a vertex V, V is a cut vertex if and only if there's a proper one separation where that vertex V is the unique middle vertex. And you see, again here, the main thing that's happening when we're doing separations is we're always splitting things into two parts. Right? So kind of the same thing for this cut vertex as it was in the disconnected case. So like kind of by default, when I go to think about a graph and maybe a connected graph with a cut vertex V, well, you delete V, maybe you get many components. But when you go to describe a one separation, you're sorting them. You're just thinking about a way of dividing a graph in two. And part of the reason that separations are so nice is that usually that's what we want to do. We want to take the graph and split it in two pieces. Okay, so we have some more sort of theorems, nice theorems coming about these this concept of a separation, but I think I'm going to stop this this batch of notes right now.